Okay. I mean, It's a great presentation. I liked it a lot. It was really good education for us.
Sorry, yeah, it was too long, but
No.
thank you. No, thank you.
Especially for such a broad audience.
Thanks, man. Okay, this one. All right. Good morning, everybody. Welcome back. Nice to see so many people here after the lovely conference dinner. Glad there wasn't too much wine or pisco sours. Well done, or otherwise, very good job. Today we have a really nice session. We're going to talk about binaries some more, so I'm very excited to welcome our first speaker, Miguel from National Astronomical Observatory, and he'll tell us about the ALMA view of symbiotic system ARA query. Go ahead.
Okay, thank you very much. First of all, I want to thank to the organizer for this opportunity. I'm very happy to be here, see the face on the papers. And thanks to everyone, because I know that it's very difficult to be here now after the dinner conference and many pisco sours. And so, okay. Well, my name is Miguel Gómez Garrido. I'm a PhD student at National Astronomical Observatory in Madrid. And I'm also an astronomer on duty at the ESO Observatory. So if you propose to this telescope, probably I have to perform the observations, okay? And today, in these few minutes, I will talk about our work studying the symbiotic star, ARA query. And in particular, I will focus on the continuum and molecular emission from the innermost regions of these symbiotic stars. So let me start with a quick introduction to our favorite symbiotic star, ARA query. This is the best studied D-type symbiotic system, which consists of two stellar components. The primary is an AGB star, a Maria-type variable with a regular period of 388 days. And the secondary is a white dwarf, a very hot and compact component. The orbital period is around 40 years, but don't worry, because Jean-Francois talked more about these parameters later. And for our calculation, for our model, we assume a distance of 265 parsecs, based on the luminosity period relation. Also, it's important for us to know the size of the Mira and the size of the orbit in the skies, because we will compare the structure detected in our map with these two components, these two magnitudes. So the Mira size is between 15 and 20 milliardsecond, and the orbital size is around 100 milliardsecond. And what you can see in this figure is the optical image of our query. And this is an axisymmetric nebula of 2 minutes in size with an equatorial ring structure here, almost in the orbital plane of the binary system. In purple is the ultraviolet emission, and in particular, this traces the jet emerging from the white dwarf. Well, we want to study molecules in symbiotic star, but there is a problem because most of molecules are photodissociated by the intense ultraviolet emission from the white dwarf, so it's very hard to detect them. However, there are few detections of CO, for example, in ARA query, and SAO and water measures in few sources. And if we want to study where is the gas, the molecular content in symbiotic system, we need maps. And there are very high angular resolution maps of SAO and water measures, as you can see, for example, here. And these maps show the typical ring structure and mentioned by Bianca and Daniel and others a few days ago. But again, there is a problem because the SAO measures only takes place under very specific conditions. And as a result, it doesn't provide a general view of how is most of molecular content in binary systems. So we need more thermal emissions, such as the CO. But before this work, there were only a few maps of CO with a low angular resolution observations. So we aim to study our query with a very high angular resolution, the thermal emission of several molecules, for example, CO, and others, SIO or SO. Then we need a very high sensitivity maps with a high angular resolution. We are analyzing ALMA observation in the band 6, 7, and 9, which correspond with this frequency, these wavelengths, 1.3, 0.9, and 0.45 millimeter. And we have also observation in the band 6 obtained with extended configuration of the interferometer to explore the most extended emission at these frequencies. After the observation, calibration, self-calibration, imaging, cleaning, we obtain maps with resolution between 15 and 35 milliards seconds. And that means that we can explore how is distributed the material in sizes smaller than the orbital size. So, for example, we can explore where is located the molecules in the intraorbital regions. We have continuum maps, and we detect more than 50 molecules, including CO, SIO, ESO, water, and one recombination line, H30 alpha. However, due to the low signal-to-noise ratio on some detection, we have only around 30 maps. Now, let's start with the results. In the figure on the left, what you can see is the low angular resolution maps of the continuum at 1.3 millimeter in the band 6. And what you can see is a central intense component in the center of the map that we identify with the emission of the AGB star and his close surroundings. In this direction, there is an extended emission. This is the jet emerging from the white dwarf. And if we compare this map with the maps of H alpha by Smith and colleagues 2017, we can identify the same structure. So H alpha and the continuum at this frequency is tracing the both components, the jet from the white dwarf. In the high angular resolution maps, again, we have in the center of the map at 1.3 and 0.45 millimeter, an intense and compact emission in the center. And if we integrate the flux in this region, we can estimate a spectral index, and we derive a value close to 2. So this is compatible with the emission of a radiophotosphere of the AGB star. And here you can see an extended component. This is probably the origin of the jet, the closest region of the jet emerging from the white dwarf, from the accretion disk. However, due to both stars are very due to the jet, the white dwarf, and the AGB star are very close in the sky, we cannot separate both components, so we cannot be sure. But if we observe few years later, because these observations were performed in September 2019, and if we observe few years later, we can separate both components because, and this shows how the system is evolving in time. This is the AGB star, and this is the jet emerging from the white dwarf. But this is work in progress, okay? Now, the results on the lines. I will start explaining something about the CO, the most abundant molecule detected in our map. It's also the most, the molecule that shows the most extended structure. As you can see in these maps per velocity channel, the emission reached size of 1,300 milliards seconds in the rate extension and declination duration. The emission is elongated in the rate extension direction, which is almost in the orbital plane. So this suggests that most of the molecular content is located in the orbital plane. This interesting emission was modeled by Bujarrabal and colleagues in 2021, and they found that probably the CO is forming part of a spiral arcs located in the orbital plane. As you can see, for example, the A component is the Myra, but the B, C, or D are forming part of those spiral arcs. And what's happened with less abundant molecules, for example, the SIO, in this case, the brightness distribution are more compact, but with some extended emission, again, in the rate extension direction. In this case, the sizes are of 300 and 100 milliards seconds in the rate extension direction. And we detect also an absorption at positive velocity that we identify with material that is falling to the AGB star, but we have to model. If we compare central channels of several molecules, for example, the CO and SIO, in these particular cases, we can observe the same structure, for example, this one here in the CO and here in the SIO, or this one here. And this suggests that probably the SAO is also forming part of those spiral arcs as the CO. Less abundant molecules, for example, SO, water, and others, so more compact emission with sizes smaller than 100 milliards seconds. And that means that probably these molecules, this less abundant molecule, only can survive in the intraorbital region, in the intraorbital region, in the regions closest to the AGB star, where they have been for, and the density of dust and molecule is high and can protect from the ultraviolet emission of the white dwarf. We have modeled the central component of the map, focusing on the 100 milliards second, and for this purpose, we use an expanding cell for the emission and infalling component for the absorption at positive velocity. The expanding cell is well determined because we have the observation well characterized. However, the uncertainty on the infalling component is high. And as a result, we don't know if the absorption is due to material that was previously ejected by the AGB star and now is falling back to the AGB star. This is predicted by hydrodynamical model, or due to the pulsation layers of the AGB star. And we can compare observation, again, separated by few years. In these two maps, what you can see is the emission of 29 SAO in 2018 and 2024, more or less. In the left, you can see the brightness distribution in this epoch, and here is the predicted orbit for the white dwarf, and here is the predicted position for this in this epoch. And again, in the other case, a few years later, the white dwarf is probably located here. As you can see, when the white dwarf is here, the brightness distribution tends to be extended to the west, to the east. However, a few years later, the brightness distribution show an extended emission located here in the opposite side. This is probably photodissociation or gravitational pull of this component, but work is still in progress. So that's all. Thank you very much. I let hear my question. My conclusion. You had a question. Thank you very much.
Thank you, Miguel. Any questions for Miguel?
Theo?
Theo.
Hi, thanks. Very nice talk. So in this system that we know, there is a very strong radiation field from a companion. Do you see any weird photodissociation products being formed, or?
We are looking for that, but there are many lines. In fact, we have some unknown detections, but sorry, you cannot see the frequency. Okay, but there are some unknown detections, and we have to explore where are located, but in these cases are over the AGB star. We have not seen any results, any molecule resulting from the photodissociation. Thank you for your question.
Other questions? I have a question, if that's okay. So you showed this material being ejected in the continuum maps. When was that taken relative to the recent periastron passage? Do you know? Is it during this?
Yeah, this is almost, you mean about the continuum?
Yes.
Yeah, this was during the periastron.
Okay.
And this other two is a few years later, where the AGB star is more or less located here.
Okay.
In fact, the continuum and the recombination lines show probably where is more or less the white dwarf in different epochs. Because, one moment, please. For example, here, you can see in red is the continuum, and in gray scale is the H alpha. So the continuum traces the AGB star and the jet. However, H alpha is only located in the jet. We have to explore in deep more recent observation to know where is the jet.
And then I also had a question about the in falling material onto the mire. Do you have velocity estimates for that? And what is the velocity range for those?
Yeah, it's a
materials?
positive velocity. Oh, okay. For example, the absorption is located here at positive velocity respect the.
And what is the?
Okay. Maybe 10 kilometers per
Okay.
second. 10, 15, maybe.
Thank you.
You're welcome.
Other questions? Okay, let's thank Miguel. Thank you very much. Okay, and we'll wait for the presentation to come up. Our next speaker will tell us about the orbital parameters of our query. So following on very nicely, and we have François Desmeurs.
Yeah. Hello, good morning. I am Jean-François Desmeurs, also from the National Observatory of Madrid. And today I will present you the latest result that our team obtained on the orbital parameter of Air Quarry. So, yeah. And so here is, well, sorry. Here is the list of all the members of our teams. So it's quite important. And so this is the outline of my talk. So I will make a brief introduction because most of the concept has just been introduced in the previous talks. And then I will present the observation that we used for deriving the orbit of the Air Quarry, and then my conclusion. So why are we interested in symbiotic stars? The evolution of AGBs to, how to say that? The evolution of AGB into planetary nebula is still poorly known, and especially the shaping. And if we don't know how to pass in a few thousand years from a star that present a spherical symmetry with a slow expanding wing to planetary nebula that are most of them axisymmetric or multipolar or elliptical symmetry. And several mechanisms have been proposed to explain that, like the presence of rings close to the post-AGB object, or the influence of a magnetic field, or the presence of a binary system. So here I will give you some insight of why interesting as to binary system. In our galaxy, only about 50% of the stars are single stars. All the others are binary or triple star or even multiple systems. So this must be reflected also in AGB and in planetary nebulas. The detection, as we saw in the past days, the detection of a binary system in AGB is very, very tricky. Because of their brightness, because of the pulsation, it's difficult to trace the binary companion. So maybe it's not a good way to interest us directly to a binary in AGB. And in 80% of the planetary nebula are not spherical. They show axisymmetry and or point-like symmetry, and so we have to explain that. And if we look at the high-resolution images that we can get from new instrument, we start to see in many sources rings, spiral, even in planetary nebula like the red rectangle, for example, or this one, we see some structures that are clear signposts of the presence of a binary. So the problem is that as we cannot really directly extract the component of a binary in the AGBs, and especially to model it correctly, we need the orbit of a two companion. It's where the symbiotic stars can help us. Of course, symbiotic stars will not produce planetary nebulae, but they do produce bipolar nebula. And so because of that, we decided to try to observe one of the most famous symbiotic star, Aerocory, that have been observed from 100 years. And I will not present it, as Miguel just told us a lot about it. Will just mention that from the last axisymmetric protoplanetary nebula, the latest distance estimate that I will use in this talk is from LIMET, that give 260 parsecs. Yeah. So it exists a lot of observation of Aerocory, but there are not so many observations that we can use to derive to image the system with a good position accuracy, and that we can use after to derive the orbit. So the first one that we used is this image obtained with a VLT sphere simple. The article was published by Schmidt in 2017 and correspond to data taken in 2014. And we can see here the Myres, the AGB stars that in the rest of the slides will be always at the 0, 0. And here we have in H alpha the white dwarf that is a bit elongated. So this will be our first epoch. Then, then we have, I think, it missed one. Then we have some observation made by Valentin Burjaval and published in 2018 with ALMA continuum at 3045 gigahertz. And we can see here also the Myra with with an extension. We suppose that the white dwarf is here, and these arcs, I don't know, we don't know exactly if it's mass transfer or not, but well, we plus, in that case, we plus the white dwarf there. Then we have the also observation with ALMA that have been shortly presented by Miguel in his talk. At that epoch, we were close to the periastrum, and it was very difficult to separate the Myra from the white dwarf because they were one in front of the other. So in the continuum, it was a nightmare. Here, it's H30 alpha that, as Miguel said, it was the bipolar outflow. So in that case, we suppose that the white dwarf was in the center of the outflow. So one more point. And then Javier Alcolia published two epochs in 2023. The first one was from 2021. It's also ALMA continuum observation at 3031 with 20 milliseconds. Yep. So here we have the AGBs with an extension, and we suppose that at the base of the outflow, we must have the white dwarf. Of course, we don't know exactly if it's here. There is some position error, but it must be in this area. And 2 years later, he repeated the observation, and in that case, we can easily see the white dwarf at that position, and the AGB is still there. We also try to make some VLBI, global VLBI observations in 2020, that it was nearly at the epoch of the Perry-Armstrong. So in that case, we observed with all the other available antennas in the global VLBI. So we use the EVN, the VLBA, the GBT, the VLA, and at 43 gigahertz, we observed during 14 hours. With a double band with with a large bandwidth for the continuum, to a short one for the line resolutions. And we try to make, as the white dwarf and the AGB was very close, we try to make a phase referencing from the SIO maser to the continuum of the white dwarf. So we get a resolution of 1 by 0.4 meter-second. Here it's the, oops. Here it's the SIO maps that were easily detected. We mainly find two places at minus 25 and minus 28 kilometers per second. And then we try to then we try to map the continuum, and this is the first result that but the SIO maser is so strong that it completely dominates the continuum, and if we withdraw the SIO emission, well, we get only noise. So at the end, at the moment, we do not detect the continuum of the white dwarf, so we can not use this observation. But well, at the end, we have 5 really good epoch for the position of the white dwarf with respect to the AGB. Oh, I'm short in time. And so we use a program with this first point. We use a program that has been developed by Pedro Pablo Campo, an astronomer at the ORAN. And he wrote a Python, the program from scratch in Python. And his program can produce orbital calculation, ephemeris, graphical. And it implemented the Dokobo method from, published in 1945 and 2012. It's an analytical method to obtain the orbit from a visual spectroscopic binary that require only 3 observations. So running the program, we get a set of possible orbit, and then to disentangle the orbit and get the one that we want, we need another input. It can be the parallax or screwing mean, but in our case, we use the variation of the radial velocity, because at EBS, we have a monitoring of SIO maser for more than 20 years. And the last one is done by Miguel for now 8 years. He observed every 3-4 weeks. And so here we have at the bottom each tick is the maximum of the AGBs. The green line is the system velocity, and the red point are our data. And what we have made is to average all the spectra from each pulsations period, and we took the velocity in the intermediate value between the extreme. So with that, we go back to the program of Pedro, and we find these new orbital parameters with a period of 39 years, a Perry-Armstrong in 2020.3, an eccentricity of 0.4, a velocity of minus 24.9, a semi-axis, and etc. But also we can derive a mass of the systems. And so we get for a total mass of 1.69 using the distance of Linnet. By the way, if we use the distance proposed by Gaia or Hipparchus, we find some mass that are completely unrealistic because we find a fine 5 dot, whoops, it's not mine. From the mass of a system, we can also deduce the mass of AGBs and the Y drive. That would be 1.14 and 0.55. And so this is nice because it's consistent with a Y drive of 0.5 solar masses. This means that the progenitor of Y drive should have had something like 2 solar masses, so it has a faster evolutions. It tells us also that it will not explode because it's too far from the Chandrasekhar limit, so it will remain as Y drive. And the AGBs with a mass of 1 solar masses will evolve to also to a Y drive, and certainly at the end we will end it with a double degenerated system. Thank you for your attention.
Sorry. Thank you very much, Jean-Francois. Questions? We have time for one quick one. Go for it, Theo.
Hi. So it's a surprisingly eccentric orbit that you get. Do you see variation in like this recombination line emission from more accretion when the companion is close to the Mira? Or?
No, I don't think so, no.
Is the accretion rate constrained in any way?
No.
Okay, so we'll keep to time. Thank you very much. And we'll go to our next speaker. Thank you very much. Thank you. And our next speaker will be Leen Dessin, and she will tell us about evolved stars in motion, mapping the orbits of close companions around AGB stars. We'll just wait a second for the presentation. There you go.
Okay, thanks, Shazreen. Indeed, today we'll talk about the title you can see here, and I will keep to that talk or to that title. Maybe there will be a slight addition in the end, but then I will look to the share whether it is still allowed or not. So why do we want to map, or at least this was the title, mapping the orbits of close companions around AGB stars? So the question we want to answer is, why do we want to map them? And can we map them? Since, we can have our science goals, but it also should be feasible given the instrumentation that we have. First, we go to the first question. Why do we want to map the orbits of AGB binary companions? And the main reason thereof is our question, or quest to what are the wind mass loss weights. And we all know, and I don't have to explain that to this audience, that there are 2 main methods to derive the mass loss weights of AGB stars, also of red supergiants. And this is a picture taken from the paper of Sophia Ramstedt. You can see at the top carbon monoxide lines, at the bottom SEDs, and both of them can lead to a mass loss weight. The upper one, the gas mass loss weight, the bottom one, the dust mass loss weights that we then transfer towards the gas mass loss weights. So that kind of methods have been used quite frequently in the literature to analyze larger samples of data. If you do that, then you know the stellar mass and temperature, you can relate the outcomes towards things that people that work on stellar evolution like, being a very simple analytical description that links your mass loss weights towards the stellar parameters. And these are then these key ingredients that go into codes such as the MESA stellar evolution code. Now, if you look, I only have displayed there of shown there two, there are plenty of them. Now, if you display all of these mass-loss weight relations in one graph, you see the following. You see that, so I have a left and a right. To the left, you have when I take the mass constant, to the right, when I take the effective temperature constant. The main message here is that if you look at all of these descriptions, be they derived from observations, from theory or semi-empirical, you see huge differences, 2 or 3 orders of magnitude. So what to choose if you would like to model your stars via MESA, for instance, depending on which one you take, you can have a completely different outcome. So if Amanda has once asked me, which one should I use? I said, I don't know. You know, it may be dependent on how many thermal pulses you would like at the end, but this is not how we do science, isn't it? Now, the main question then is, why do they differ? First of all, for sure, we know that if we use mass-loss weights from ACDs, we have that very uncertain factor of the gas over dust ratio and of the gas versus the dust wind velocity. That can easily give you an uncertainty of a factor of 30, 50, whatever. But there's more in that than only this. So the main thing is then and this I will show you in the next slides, we are analyzing our data in a too simplified way. Since we often, and all of us like to use, and we do, you know, this one-dimensional stars. But this is not the real life of an aging star. We know that the surface convections can have the bubbles. When we look at larger scales, and this is an image from Theo, we see that dust is forming in more cloud-like or bubble-like structures as well. We have large-scale structures already shown by Thaisa. I think it was Thaisa yesterday. And we have also that we have the bow shocks. That's a bit similar to what Hans has been showing, but then here with the Galax data. The main focus of the things I will tell you about is this third picture. These large-scale structures of which we are now quite convinced that we know the origin. I say quite convinced, since most of our stars are never alone. And indeed, we all know the statistics. We always say, yes, 50% of our solar-like stars have a potential companion. But I think literally that this is underestimated. Since we have done this ALMA Atomium Large program, and we were just trying the main core ideas, understanding the astrochemistry in evolved oxygen-rich stars. But when we got this beautiful ALMA data, we were seeing all kinds of structures which we didn't expect. Now, the order of the data, of the images that you can see here, is not random. The data have been ordered from top to bottom, left to right, with increasing mass loss rates. So the main thing that you can see here is that if you increase the mass loss rate, particularly at the bottom, you get these more regular-like spirals, while for the lower mass loss rates, you see much more complex structures, which is far more difficult for us to understand. The most easy ones are the bottom ones, the spirals that can come from the interaction with your AGB cell. So the idea there is that indeed what we see here is an interaction with a companion, long period systems, orbital periods above a year, orbital separations above roughly 2 astronomical units. The main thing as well here is that we were saying in the beginning, well, this is an ordering in terms of increasing mass loss rate. Well, the main thing there is that it's also an ordering in terms of increasing expansion velocity. Since if your expansion velocity is larger, and Shazreen has also been showing that nicely yesterday, you can have more this regular stuff, the bony hole-like morphologies that you can have. So these ones, they have such a low expansion velocity that the interaction period with the companion is much longer, and you can get all kinds of complexities. This kind of data has induced a lot of new effort into modeling. We have seen already quite a lot of nice results yesterday, so I will not repeat that. You can have the spiral shapes, you can have the circumbinary disks. You do see here 2 examples of grid-based codes. I have taken them by purpose, since we have seen a lot of SPH yesterday, of Chen et al., and to the right of Ilek. And then indeed, the one SPH simulation of one of my former PhD students, Yulin, where we have a triple system and where we can have a kind of an even odd-like simulations, if they are true at all. Now, this is hydrodynamics. This is not the end of the story. And as Thijs and Marie have been saying also, as we also have seen yesterday by Camille and Owen, when you have the dynamics, you still need to implement the chemistry and then do the radiative transfer. And this is what we're currently trying. This is an older image. I will show you a more recent one later on, where Jan Bolt and all of our colleagues at KU Leuven have been trying to cobble the things. This is a grid-based code. It's MPI MRVAC. It was then coupled with Chrome. Simulation times are enormous. And we had a star that was pulsation period of a year. And then after that, we were studying what we can see. But if you have a pulsation period of a year and an orbit of 10 astronomical units, you can see, this is the pulsations that you can see here, the pulsation ripples, what a kind of a complex system you have. If you then do the radiative transfer to the whites, then you start wondering if you have different inclination angles, what you can see from the top to the bottom, you can have all kind of different morphologies. And then the question is, can a partner change your life? I think we all know the answer. Yes, it does. Since if we deduce from these observations the mass loss rate for including the companion, we have a mass loss rate of around 5 × 10⁻⁶. If we do the same simulations without the companion, the mass loss rate is roughly a factor of 6 lower. This has important consequences, since it implies that our mass loss rates have been overestimated if we are using them as being single stars. So we are wrong. And now I want to also show you these new results of Florian. Florian unluckily could not attend. His mother died some 10 days ago. So that is why I really want to represent his results here. So Florian is continuing on that research, not only for circular orbits, also for eccentric orbits. This is again grid-based, and you can see here that we have taken a star or a companion that can also explain these long secondary periods, but that's another story. Only 0.1 solar masses, and this is now the image of the velocity for the eccentric model, and we have measured the mass loss rate at 10 astronomical units and at 30 astronomical units. Since where to measure? This is also what Hans has been showing. You don't want to measure in a bow shock, but so you need to take that at different distances. And now I build up the slides. So this is the outcome for the shell at 10 astronomical units to the white for 20 astronomical units. We start always without a companion, and then the companion appears. So you can see at 10 astronomical units, we start around 5 × 10⁻⁷, and then when the companion appears, we have an increase of a factor almost 2. The same, but at higher values when you do that at 20 astronomical units. This comes from the higher velocity we have there. And then the question is, do the same simulations, but just have an eccentric orbit. And then you see the following. We have an increase of a factor between 5 and 20 of having a system without a companion or having a companion, a very small companion, with that eccentric orbit. So this is almost dramatic. They have such a huge impact. And this is also what Chazrin has been saying yesterday, where even the companion had a much lower mass. A factor 5 to 20 is a lot. So I think just that this classical picture of pulsation enhanced dust-driven winds is not complete. And so if you go to our mass loss rate prescriptions, this is the classical picture of Vasiliadis and Wood. And if I now indicate which ones we think or we know are binary companions, there's nothing left. So we have just to redo our whole analysis. So do we understand these mass loss rates and their relations? I don't. You take your own conclusions. Can we tackle the problem very shortly? Yes, we have one, but crucial observation. This is the nice data that is represented by Mats Asselders in his paper that was published last week in Nature Astronomy. Take your time to read it. take a lot of time, since it's 116 pages. So this is the ALMA data from 2019. This is the new ALMA data from 2023, where you can see that the secondary blob that is here, and of which we were not sure whether it would be an outflowing dust cloud or a companion, has nicely moved around. And here you can see the trajectory through the plane of the sky, the proper motion. We can combine that, I zoom out, with Gaia and Hipparcos data, and we can do the modeling of the orbits of one versus the other and deduce full Keplerian solution of the whole system, including the proper motion. We have also combined towards a parallax and the system parameters. We see it is an orbit, it's a circular orbit. And then I go to the results of Yoshi and Amanda. They also have played a crucial role here, since they have used the data set to also, from the pulsations, deduce the mass. And what you can see here is that the pulsation mass, here at the bottom, is slightly higher than our dynamical mass. This kind of studies will help us in also improving the stellar evolution models, since we have two independent constraints of the current mass of a system. And then to end, go and read Mats' poster. We have achieved a lot of nice results predicting what the system will do in the future. We predict it will merge. We also have looked, and this is what Mats has been telling you, that we think that the system had originally also roughly a circular orbit. We are not really sure whether that's correct or whether we have a problem with our models. So to conclude, what you can see here, and this is the next step, we did have already quite a lot of data from, this is a paper from Alan Jorison on eccentricity versus orbital periods. We did know already what we can have for these diagrams for the earlier stars and for the progenitors. And now we have added one star, only one, but it does show that potentially there is a eccentricity generating mechanism at the end of the AGB towards a post-AGB, and that will be addressed maybe by Hans tomorrow. Thank you.
Summary.
Thank you very much for that talk. Any questions? We have time for one quick one. Hans.
Yeah, thank you. Very interesting and disturbing. But so what is the actual mechanism that changes the mass loss rate?
It is just the fact that the companion has an impact on the gravitational potential. So if you have your companion...
Sorry, I have to change that.
So it is, you can just compare it a little bit, Hans, with either you have a single star and then your material needs to escape the gravitational field from your single star. But if you have a companion there, it also sucks. And so that's just a simplified picture that you can have. But the main, let's say, when you describe it physically, it is since you have your gravitational potential between both stars that is acting as well.
Can I add a quick one?
Yep, quickly.
So am I right to conclude that this mainly affects lower mass loss rate stars? If you go to the very high mass loss rates, the effect may not be that large.
I don't know. I'm not sure that this is correct what you say, since it will all very much depend also on the mass of your companion and where it sits in terms of orbital separation. But we saw the one that you have seen here was 10 to the minus 7 up to 10 to the minus 6, so that's still lowish, right? But there already the impact was a factor 5 to 20.
Okay, I'll just make a quick point about this one point. If we take the symbiotics and we plot them on the same space, and we already heard about one nice one, so those stars can fill that space and they have the same problem with the eccentricity. So, and I think, Hans will show that. Okay. Cool, good. Thank you very much. Thanks, Lian. And now we'll go to our next talk, our fearless leader. We have Claudia Palladini who will tell us about unveiling the origin of asymmetries in AGB envelopes with VLTI and Matisse.
Hi. So yeah, no lock announcement right now. I will talk to you about science, and I will give a bit of introduction to basically the next talks that will follow after me. This is still a work in progress. We have a lot of data. I will just show some of them, and I will stay quite qualitative because that's where we are standing still right now. Well, following up the rest of the program of this morning, the question we are trying to address here is also how does nature create the shapes of the post-AGB when the AGB looks like. Well, I have to say in the last 15 years, the picture of the AGB changed quite a lot. Yeah, so we are on that way, following that wave. In this talk, I will focus on the part which is highlighted into the graph. And it's basically, we are between 1 and 10 stellar radii. And the data that I will show you are the data from the Very Large Telescope Interferometer. So we move away from ALMA, where this community is super involved into. And what we are after with this program is to hunt the elusive binaries. And we know there have been a lot of detection systems, techniques that we used. Well, binaries have been detected via symbiotic activities, radial velocities, a photometric campaign with a long secondary period, astrometry. Lately, in the last 15 years, we started to use ALMA, and in general, anyway, sub-millimeters and radio interferometry. And what we are after is the population of the closed binaries. Closed, like P1 GRUIs, meaning within 10 stellar radii. And for that, you need, of course, high angular resolution. I want to show you this first, which is where I started from, which is the inheritance of the VLTI MIDI large program that we published in 2017. MIDI was the predecessor of the instrument that we used for the next data we show you, where we didn't get images. And so we found from the sample of, I don't remember if it was 10 stars or maybe a bit more, that basically we were mapping asymmetries without knowing what they were. And we found that basically they develop already at few stellar radii. Well, now it's not a surprise anymore. We didn't know what they were, though we could guess convection, clumps. More evolved stars for us were showing more asymmetric environments. And we were observing a subsample of the mass Herschel program. And at that time, we detected that asymmetries were more often observed in the Herschel so-called fermata targets. So this is where we started from, and what got my attention and what I was always very curious about is the point, nature unclear. I wanted to see the pictures. And so the BIN-AGB large program, it's a program where we had 180 Matisse hours of Matisse time to image in detail 10 AGB stars between 3 and 13 micron, more or less. Then we had to cut it to 11.5, but well, that's another another discussion. And the question we wanted to answer is, what is causing this asymmetric outflow? And then even more, what is the dust mineralogy? And do we have disks of signatures of binary? In the making and in the developing of this work, here I'm putting my hat of instrument scientist, formal instrument scientist to Matisse. Basically, Matisse came online in 2017, so we were still at the first years of this instrument. And I don't know if you, for the people that have ESO data, you will see when you receive your data that there is a grading system that the observatory use, and you have A, B, or C, where A, B, it's like you have very good data, C, it's like, oh, I observed crap because the weather was bad or whatever, and so your data go back in the queue. And what we were observing when we had a very simple system of grading the data at the telescope. But with this large program, what we observed, actually, I had some of the students, like at that time, students, Leo came to me and said, you know what, the observatory graded this data A, so they are great, but to me, they look very bad. And that was because we had a very simple, basic way of grading. And this was changed then, thanks to the large program. So sometimes it's good to have instrument scientists that are active also with their instrument. All of this to tell you that if you notice, if you are an observer, you have your data and you notice any discrepancy between the data quality and the observatory, please close the loop, come back to us and let us know so that we can improve that. Okay, so when we got the data, what we do usually after developing, by the way, this quality control system that we developed from the previous slide, this will be publicly available. So it's now integrated at the observatory, so anything that you get after 2022, it's already clean. But if you have data from before, you can use those codes to clean it. So something else that we did, always in terms of helping the community and making things accessible to everyone and tools. Julian Drevon, that is sitting there, developed a tool which is a Python wrapper for the image reconstruction. Image reconstruction in our community of interferometrists in the optical infrared, it has been always a very tricky business done by very few people. And now, thanks to this tool, which is publicly available, you can run it almost safely. And this is publicly available. And so in the future, the next tool, so I will show you now some images, but in the future, the next things to do is to use model atmospheres. So the first slide is for the work of Leah. Leah will tell you all about this star. When she came to ESO to work on V-Hydra, she was looking for the binary. She came with the orbital solution. And when she got the image, she was super depressed because she was like, oh my God, I got a blob. Then she looked a bit more carefully and she said, oh no, that looks like an avocado. Avocado in Chile is called palta. And that's why we adopted that little avocado up there. As a symbol for our program. Thea will tell you everything about this star, but basically notice that in the Palta shape, the binary is in that circle. And something interesting is that we found that there is a clump of dust next to it, and it's mostly SiC dust. This is the work that Julian will show you. We have another kind of, well, you can imagine another Palta there. This is P1 Gruis. That's where the position of the binary, and on the left, you have our Matisse image overimposed to sphere, and well, Julian will tell you about it. Then we have the case that was analyzed by Vlad Rassau. He's not here with us. He's finishing his PhD. He was analyzing Xtra, and he found something which is spherically symmetric and sits nicely into the overall convection, pulsation, dust-driven wind. So we have some stars that look normal. And then there is something super interesting that Jaime now is working on, which is this star where you have the star, and we detected some blobs on the side, which are consistent at all wavelengths. And then we thought, like, we saw this beautiful picture, the beautiful simulation from the Uppsala group that Joaquin was showing us. We were like, well, maybe it's a single star doing that. The thing is that that structure is sitting there since 15 years. So stay tuned. We are trying to figure out what it is. And these are some other examples. These are stars that are further than 500 parsec. So we are looking, the star is a bit smaller inside there, but there are a lot of strange structures and that can be observed. So to summarize the morphology, at the beginning I thought like the first one we could call it Roche lobe shape, but Roche lobe is something with a physical meaning. So that goes for the moment as a Palta shape. So we have stars where we know from radial velocity that we have the orbital solution, so we know where the binary is, and we find this kind of Palta shape. Then we have something which is spherical. We have some stars that are bipolar. We have 3 of them. This is the more, well, the one with the best data set, the one we show here. And then we have something which is more complex. The question is, I think that we have to go back or push more for the time resolved data. Because lately we keep getting one picture of things, one picture with ALMA, one picture with VLTI, but I think it's time that we go back to the time resolved data. As I was mentioning, basically, this is a very complex and rich data set. We are just scratching the surface of it. It would be nice to have more time domain resolved spectroscopic observation to try to get the binary solutions when possible, and we have modeling pending. Take-home messages. AGB stars may be very asymmetric within the first few stellar radii. Okay, we know that. But what is causing this outflow? We have the interplay between convection, pulsation, dust formation, and the stellar wind. But we do have also presence of companion, and we do see those ones within the first 10 stellar radii, and it can be very dramatic what they do. We are thinking that maybe there are some disks there, but maybe they're bipolar outflow. How do we distinguish? Again, I think multi-wavelengths and time-resolved observation. Dust enhancement is observed next to the companion, so it's not wholly with the ALMA. We see consistently that also the VLTI. The next thing we are after is the dust mineralogy next to the companion, because we see SiC overabundance and silicates, so we will look into the modeling. Dust. If you liked and enjoyed Chile this year, you may want to come back next year. We have 2 conferences upcoming. One is in the Atacama Desert in San Pedro. It's about type 2 supernovae, but it's also about supergiants. And the second one is Infrared 2026, where we will showcase science and synergies in the thermal infrared. MIRI, METIS, Matisse, everything that, Spitzer, everything that is at those wavelengths. I will not organize any of this, but I might be there as a participant. Thank you.
Thank you, Claudia. Your questions?
You can keep the questions for the people talking.
Oh, okay. Go ahead, Angela.
This might actually be a question for Leah, but as always, I want to know what optical constants you're using. So you say that it's the lobe on the Palta is, which honestly, Palta is fabulous. That it's almost all SiC, and that's like, even when we look at carbon stars, you don't need much SiC to see the features. So I'm just curious what you're using to model that.
So we are not modeling. We are still on the, we look at it, we know that 11.3, there is SiC, and that's where we said, this is in the SiC feature. And we were looking at the other wavelengths where that is a bit less pronounced, but it will come afterwards.
Oh, yes, go ahead.
Yeah, so this is not an online question, but a question from myself. I was wondering if you have any clue on where on the, if there's any relation on where on the AGB is with respect to these shapes that you find. Do we know the evolutionary states?
Okay, so some of these stars, so we have semi-regulars and Miras. So what you see here, I think Vihydra is a Mira. Do I remember correctly? Yes, Vihydra is a Mira. Then we have in the sample R4, II Lupia, these are all carbon Miras. And then the others that you see here are semi-regular variables. And they are the same from the MIDI program. So we have them mapped in the IRAS color diagram. We have also stellar parameters. So that will be something that we will follow then to see how these asymmetries and how these things show up.
Good. For the pulsar one, what's the separation between the components? Or is it coming?
Yes, it's coming. So Leah,
finally.
Leah will tell you everything.
I'm looking forward to it. Okay, let's thank Claudia again. All right, and our next speaker will tell us more about V-Hydra. Leah will tell us about a search for AGB binaries and their imprint on the circumstellar environment. Leah Plankert. Coming. Yeah, there you go.
Hello, everyone. So I couldn't have dreamed a better introduction of my talk. So I will speak about AGB binary, but focusing on one target. So I hope at this stage of the morning, you are all aware that we are looking for AGB binaries, but we do not have a lot of them. We are quite aware that they are needed to explain some of the circumstellar morphology that we see on the AGB star, and that on an evolutionary point of view, you know that the later stage, as you will learn more after the coffee break, have a lot of binarity, but we have only an approach of case study for AGB binary. So you have learned about some of them this week. So you have the one that Thaisa mentioned, W equally. You have air aquary that was introduced by Jean-François some minutes ago, then PyGru introduced by Lane, that is the shorter period that we have, and that Julien will explain a little better. And in this talk, I will focus on V-Hydra, the only carbon AGB star with a binary companion that we have. So the idea is really for this star to derive the orbital parameter and link this orbital parameter, this orbital motion, with the large-scale morphology. So we know that V-Hydra is a carbon star, and the suspicion of binarity, because we first need some guess to know which are the better star to study in detail, come from the light curve. So the light curve of the star has what we could call a long secondary period, but way larger than what we see for common LSP from the D sequence of 17 years. And on the top of that, the star has also a UV excess that cannot be explained by the AGB itself. As Jaime had mentioned, UV excess is often a signature of a binary companion. And on large scale, the stars have been imaged quite a lot of time with ALMA, and they have a really complex morphology. So here you have a sketch of the 3D geometry of the system. You have a dense equatorial wind that you see on the CO line and the fast bipolar outflow with velocity up to 200 kilometers per second. So what we want to understand is what is inside this nebula and what is shaping the system. Is it one star, two stars, how the stars are interacting with each other? So I will present a two-chapter study focusing on really the aspect of using multi-instrumental analysis to retrieve that kind of parameter. So the first one is the temporal constraint that we can have from spectroscopic monitoring, and then the spatial constraint at really high spatial resolution with interferometry. So going on the temporal constraint, we use spectroscopic monitoring for more than 10 years with Hermes spectrograph on the Mercator telescope. And from that, here is really like the state that we can derive from the radial velocity curve the orbit of the star. So you can see that as the star is a Mira, from the radial velocity curve, you have variation due to the expansion and contraction of the Mira. And on the top of that, you have non-eccentric, a circular orbit that you can fit with a period exactly of 17 years, so corresponding to the period that we see on the light curve. Combining this radial velocity curve with astrometric indicator, as Lynn has just explained, we can retrieve the full orbital parameter, because with the radial velocity alone, it is not possible. And we can see so that the orbit is circular with the period of 70 years, an inclination that is consistent with the large-scale morphology, and we can have an idea of the mass ratio between this, and the companion is expected to be a main sequence companion. What is really nice to see also is that the obscuration event that we see on the light curve correspond to what I call the superior conjunction, so when the companion is in front of the AGB star. So this is this configuration. You are here, you are looking at the companion, and here you have the AGB star. And then there is one step more we can do with the spectroscopic monitoring is look at signature of interaction between the two stars. And in fact, in one specific line, the sodium doublet and the potassium doublet, so really resonant line that are excited at really low energy, we see a variation of the blue shifted absorption depending on the orbital phase. So here at the conjunctions, superior conjunction, you have velocity, a blue shifted velocity up to 200 kilometers per second. And then at the opposite phase, you have some kind of pseudo emission due to the carbon star and lower velocity absorption. And you can do that at all the phase. And you have some kind of nice variation, smooth variation of this blue shifted absorption. And this kind of thing is quite regularly observed in post-AGB binaries, as Hans will explain to you tomorrow in H-alpha profile of post-AGB binaries, and can be modeled. Here we did some kind of simple spatiokinematic model by a jet launched by the companion. So if you do some kind of simple spatial kinematic model, assuming a density and fitting a density and a velocity profile of a conical jet launched by the companion, you are able to reproduce that kind of profile, meaning that we have some kind of velocity jet launched by the companion, so a blue shifted cone that we see in the optical data, and we can assume by symmetry that we have also a counterpart that we don't see in the optical data. And combining this picture, so this picture from spectroscopic monitoring and this dynamical picture of the system with the orbital inclination that we have, we can link this to the shape at large scale that we see in the molecular line. So we have a consistency in the velocity and in the axis direction between this jet that we derive from the spectral line with the large scale morphology in the molecular line with ALMA. So that's for the first part, the temporal constraint on the gas and the orbit. The second part is what about the dust in the system? Where is the dust located, and what is the impact of the companion on the dust at the innermost scale? So for that, we use, as Claudia introduced we use Matisse data to image the star in the L and N band. So the star is quite dusty, and it's a carbon star, so it's made mainly of amorphous carbon with really small grain and a little bit of silicon carbide grain. And we image the star in the L band, so mainly in the continuum, and in the N band in the dust feature emission. So what we can see is that the star is quite asymmetric. You can see, for example, that in the L band, we have some kind of asymmetric intensity distribution, but really restricted to the expected size of the star, meaning that this kind of bright and darker spot that we see could be due to opacity effect on the stellar surface. While when we go to the N-band data, you can see that we have some larger emission, especially more prominent in the close to the silicon carbide feature. And this extended emission in the northeast direction is larger than the expected size of the star, meaning that we have some kind of extended emission. And as Claudia showed you just a couple of minutes ago, if we combine those two images, we can have this kind of palta shape, where you have in red the L-band data and in bluish the N-band data, and then we can compare it with the orbital solution that we derive. And well, we do not have a perfect match, but some kind of match within the uncertainty of our system, because we have still some uncertainty on the exact period, plus minus 1 year. But according to that, we have an idea of where the companion is, and this is consistent with the blob that we have. So this kind of dust clump that we see close to the companion is likely to be explained by the presence of this companion. And it could be like a dust cloud around the companion, an accretion disk, dust stream, I don't know, but something linked with the companion. And this answered the question that I had at the beginning of my talk: what is at the really innermost edge of the nebula that we have in the system? So here you have the image with ALMA, and then I will here let an open question. You have here concentric rings in the system that are spaced by several arcseconds. So that would correspond with the expansion velocity of like hundreds of years apart. And this ring cannot be explained then by the orbital separation, because we have a circular orbit and we have a 17-year orbit. So those rings are still unexplained. They cannot be linked to the thermal pulse. They cannot be linked to the orbital motion. So open question on the morphology of the system. So yeah, I will here let the take-home message and take the question.
Thanks, Leah, for that beautiful data and talk. Questions for Leah? So can I ask my question then about the separation between the two
It's
if possible in AU?
yes, 10 AU separation.
10 AU,
Yeah.
okay. It really looks like wind-Roche lobe overflow, like
Yeah.
filling the Roche lobe, and so I think it wouldn't be bad to call, but I like the avocado bit. But it really does look like the system is filling its Roche lobe and then being transferred to the companion, and I think it looks really, really nice.
Yeah, I think if we have like epoch data, it was Matisse, so second one, we could confirm the shape and be able to assess the mass transfer there. Yeah.
Yes, go ahead.
It's not a question to Leah, it's just a comment. I wonder at a certain point if we start detecting, if we keep imaging objects so nearby, we keep detecting those kind of shape, can we then infer that there is something there? Of course, you need the confirmation from other data, but yeah.
And the separation, oh, sorry, go ahead, Theo.
Hi. So I was wondering, I don't know much about dust in carbon-rich sources, but in oxygen-rich, we have this idea that you form aluminum oxide still in the extended atmosphere, and then silicates come further out. Could it be the same with SiC, that it is in the extended atmosphere, and what you're seeing is a deformation of this extended atmosphere, that's why you see so much SiC there? Or have people determined that SiC is actually in the outflow and not in the extended atmosphere?
That's an excellent question. And I don't know the condensation temperature between amorphous carbon and silicate carbon, but I would say that this is the parameter that will determine where it is within the system.
Can I add to that? There's actually pre-solar grain evidence for how the system should work for the grains that we have. Whereas other carbides like titanium, ruthenium carbides are often seen as cores of carbon grains that come from AGB stars. The silicon carbides are never coated in carbon, which suggests that they form after the carbon.
Any more questions? Anything online? Good. All right. Thank you very much, Leo. All right. And we'll go to our final talk of the session. We have Julian Drevon, and he's going to tell us about mass transfer and dust formation in the presence of a binary companion in the heart of Paiwan-Gru.
Thank you very much. Hello, everyone. So, yes, today I would like to indeed talk about this PIGRU system that has been widely referenced in this conference within the framework of the AGB, the BIN AGB large program led by Claudia. So let's talk about PIGRU system first in the first glance. So it's been a while that we know that we have a binary system, in fact, in PIGRU. So we had a companion at further away, around 3 arcseconds. And we also know that we have these pair arms. But in the paper of Meyer et al. In 2014, they said that no, the spiral arm that we see with this companion cannot be induced by this companion. It's too far away from the star. So these spiral arms are indeed, in fact, produced by a closer companion around 40 mass, about 40 mass from the central star. That should be around something here. Okay, so that was in 2014. Here you have, by the way, the ID card of the main star. And in 2020, we had Oman paper that show ALMA observation with indeed the first direct images detection of this close companion at about 40 mass. And like 3 years after, we had this paper of Miguel Montarges that show sphere data with a clear at larger scale, with a clear dust environment in the form of like a beginning of the spiral arms that was basically matching the position of the companion. So yeah, so basically the question that we are asking and the information that we are missing is how this just the third companion, we call it the Pygrusi, is in fact changing the way that the molecules and the dust are formed in the close environment of this star. So this is a question that we want to ask with the Matisse observations. That's why we provided images. So these are the Matisse images that we have. So in the top part, you have the L band images that shows mostly molecules. So you have the pseudocontinuum here and different rotational, vibrational band ends of the SIO here and here. And on the bottom side, you have end band images with still some molecular information that domain this at shorter wavelengths, and then the dust. So what is mainly formed of alumina and silicates. Then, since we have those images, I wanted also to overplot on those images the orbital solution. So currently in the literature, you have to know that we have 2 different orbital solutions that dropped out this year. We have one from Miguel Montarges, and the second one, by Mats Esselders. So I recommend both posters to look at, by the way. And here we decided to put Mats orbital solution because it cops more it fits more to the images, basically. And here you have, so in full line, you have the orbital, so the path of the binary. In blue here, you have the expected binary position at the time of the Matisse observations, and the arrow is showing you the direction in which the binary is moving on this orbit. And in dashed lines, you have the Roche lobe of the system, of the 2 stars. So now let's talk about what are the different features we are seeing both for the molecules and for the dust. In L band, what we are seeing is clearly a non-uniform stellar surface, so either due to some convection or change of opacity in our line of sight. We see a disk-like structure at the exact position where the binary is supposed to be. And if you subtract the continuum to the SIO image, you have this image, and you see clearly that the atmospheric SIO extension up to 1.5 stellar radius is also shaped in the direction of the binary. In N band, you have, so for the molecular part, so you have water and SIO atmosphere extension up to 2.0 stellar radius. And at the exact position of the binary, you have this disk-like structure, which is also visible, a bit more blurry because, I mean, the resolution is not the same also that in L band. And made also of those kind of type of molecules. And then for the dust, to finish with this, we have compact extended dust of alumina atmosphere at up to 1.5 stellar radius. We have a disk, so the disk-like structure made of alumina and 3 silicates at 3 stellar radius, which is once again aligned with the expected position of the binary. And in addition, if you pay attention, on the right picture, the right here, you have the starting shape of a plume-like structure. So we will try to interpret all of those different features to have a scenario, scientific physical scenario that could explain what we are seeing here. And then Windrush lobe overflow. So let's, I mean, the talk was of Shazren was amazing. So let's have a short just overview applied to our system about this Windrush lobe overflow. So to have a Windrush lobe overflow, you need a binary system. This, I mean, okay, we have it. You need to have a star that does not fill its Roche lobe, its Roche lobe, because otherwise it's a direct Roche lobe overflow. This is our case also. And you need also low dust acceleration, because if the dust is forming too close from the star, then the wind has the time to accelerate when it reaches the binary potential gravitational. And if it's too low, if the speed is too low, the dust can be accreted by the potential gravitational of the binary and form those kind of disk-like shapes that we are seeing in our system. So basically, this Windrush lobe overflow is divided in different steps. So the first step is you have basically the molecule that forms close to the star. So you have an elongation of the atmosphere facing the companion in the direction of the companion. So we have this extension visible in the direction of the companion in L band, so for the molecules, but also for the dust. Which is consistent. Then, once you have done this, the second step is basically you have the molecules that start to be triggered by the wind that we are seeing here, and then you have the disk of dust and molecules that start to form around the binary. And if you zoom a bit, which is under the element of resolution that we have, that's why we don't resolve it much. But if you zoom inside this disk, at the exact position of the binary, expected position of the binary, you see a hole. Thanks. You see a hole. So we think that this hole is real because we make tests with and without this hole. We need this hole to produce our observations. And we think this is because we are facing high temperature of this accretion disk here, close to the companion. And that's why we have this hole inside this disk-like structure that we are reconstructing. And then the plumes. So the plumes, we think that it's indeed the starting point of the spiral arms formation that we expect for those kind of system. And because, I mean, this was a super impressive picture. So thank you, by the way, to Leah that gave me this other plot. So here you see the Miguel Montarges sphere observation and our Matisse image reconstruction with a plume-like shape. So I mean, I really like this image because I mean, when I talk about it with Bruno Lopez, which is the PI of the Matisse instrument, he told me that's the reason why, one of the reasons why we wanted to build Matisse, is to do this bridge, to build this bridge between the observation that we have at really tiny scales and the one of larger scales. And here, for one of the first time, we just link the two in a coherent way. So we just rotated following the MATS orbital solution, we just rotated our Matisse observation to cope with the time of observation of the sphere of Miguel, and it matched basically perfectly. And yes, one last slide is basically the nature of the companion. So we tried, because there is still, I mean, an uncertainty about the nature of the companion. We still didn't know quite recently if it was a white dwarf or a main sequence star. And we say that, okay, so we have the ALMA observations. If the ALMA, in both cases, it can be either free emissions or thermal emissions. So in the case we have the white dwarf, we have the free emission, and in the case this is a thermal emission, we have the main sequence. But with the Matisse observation, so in N band, where we expect to see the dust thermal emission, we see a signature. So which means that if we see a signature, this is not free emission, otherwise we didn't see anything in the N band data. So we are facing a thermal emission, and therefore we are facing a main sequence star as a binary companion. And for the conclusion, so basically Pigrussy is a main sequence star. The images support indeed the Windrush lobe overflow scenario between the AGB and its companion P Gruci. And then we also detect one of the first circumcompanion disk around the P1 Gruci, and possibly a hole close to the companion in the center of this disk. And of course, the detection of this plume-like structure, which is indeed the starting point of the Archimedes arms that we observed at larger scale. So, and we will hope to have more observation to follow up the evolution of the system and to confirm the different structure that we are seeing to see their evolution. Voilà. Thank you for your attention.
Thank you so much, Julian. That was beautiful data.
Thanks.
Yes, go ahead, Lynn.
Fantastic, really. Such a nice data set. Congratulations.
Thank you.
I have two questions. First of all, I think something we can do is overlay the hydro simulations we have for the system on your data and to see, on the binary, on the spiral structure, whether that is aligned. Secondly, on the potential, whether we have a white dwarf or a main sequence star. So you now point towards a main sequence star. I think now we also have to look to Marie, since you see a hole in your data. So potentially Marie can check from her data what kind of temperature at least the main sequence star should have to be compatible with the hole that you see there in the data.
Yes, so I think we have some theoretical work. It's done by Malfait, 2024, I think. And the size of the hole, indeed, we have to adapt it to our system, but the size of the hole should be like a 1 AU, the order of magnitude of 1 AU.
Yeah, but now I'm thinking upon using also chemistry to link.
Yeah, definitely.
Yeah.
Thank you.
Yes, go ahead, please. I just need a microphone.
Oh, you can take mine.
Thanks, Julia. Very, very, very nice talk. I'm also interested in this hole, and I was just wondering if you consider doing maybe gravity observations or something like this, so that you actually get a spectrum of the hole.
So yeah, we can try this, but what I would like also to do is getting more Matisse observation to recover this hole at another phase of the orbit of the Pigrussy. But maybe you want to add something because Claudia has gravity observations.
I have 3 epochs of gravity observation, and at first we didn't reconstruct images yet. But it seems like you mostly see the star, so P1 Gruis A, like in the Pioneer data, because it's so bright that it overshines everything else. But there will be a student coming at a certain point, the student Lucia Malk from Miguel Montage, and she will work on those data sets.
Anna?
Yeah, just a quick question. Do you have an estimate of the mass, you or anybody working on the system?
Yes, you have. I mean, we can take the estimation of the mass of MATS orbital solution. So from what I remember, maybe Lynn, you want to add it, but I think it was something around 1.05 or something like this.
Yeah.
Yeah.
Other questions? I would say for the whole, also another thing to check to discriminate between main sequence and white dwarfs. Often if you can get an optical spectrum and look for flickering, I don't know how easy it is. I'm not a observer, but if you could get sorry,
I was quick.
Yeah, so optical flickering is often a good indicator from the time scale of the flickering that you get in the disk. You can tell what kind of companion it is. But I realize these are bright AGB stars, maybe at minimum, I don't know. Yeah.
Thanks.
Anything else? Yes, Theo?
This is like just based on the 4 systems which were discussed today. For the 2 that people think that they are main sequence stars, the eccentricity is 0. For the 2 that is white dwarfs, they are eccentric. Is that something that is known or is something that is emerging now from this type of data?
That's a good point.
Is this a question for me? Yes, no, because you're looking here. So
For anyone, including you.
So you mean for PIGRU itself, for the different orbital solution of PIGRU, or in general, what?
So Pi1 GRU and Vihydra, they
Yes.
seem to have zero eccentricity in their orbits and
Yeah.
they have main sequence companions.
Yeah.
And our Aquarius and Myra have eccentric orbits and white dwarf companions. Is that something that people expect or people have known, or?
I have no idea.
I think it, for the closer ones, because of tides and things like that, we do expect circular orbits. The ones that are dusty and these wider binaries with the, like Myra or Ara query, they're much wider binaries, and so there you can have a larger eccentricity, I would say. But as we've seen from all these eccentricity period diagrams, we don't understand how this is working. That was the point yesterday. Yeah. Go ahead, Javier.
Just a comment. In the case of area query, it's eccentric, which is wide, but when it comes to periastron, then it's close, which is 8 astronomical units.
Yes.
There is one difference in these objects. We have 2 objects with jets. Area query has jets, but of course, ionizing jets, then we don't see in the molecules. In Vihydra, we see this high velocity jet in CO, but not in P1 GRUIS. So that's another difference. Sometimes we do power jets with the companions. Sometimes we don't.
I think I'm going to be in trouble. I'm super excited. So now we're starting a discussion. I'm a bad chair. I apologize. Let's continue the discussion on Slack, or during the discussion section, please add your questions and we should continue this discussion. Thank you very much to all of the speakers for our session, for the beautiful data. Thank you.
Aló, aló, sí.
Hallo?
Aló, aló, sí, sí.
Okay, we should start the last part of this morning session now, please. And we will start this last part with Anna Escorza's talk. Please, Anna, the floor is yours.
Let's check if everything works. Yes. So hello, everybody. I am going to take you off the AGB phase and evolve these systems a little bit and see what happens after. And the reason why I want to do that is because AGB stars are messy. And this is not something I'm saying. This is something that you have been saying for years. AGB stars have huge convective envelopes. They have pulsations. They have winds. They have super complex circumstellar environments. So for people like me who care about the nucleosynthesis, about the fact that these stars also make about half of the heavy elements that we know, looking at the atmospheres of these stars and trying to do elemental abundances is something that only very few, very brave people do, and I'm not one of them. But lucky for me, these stars also come with company very often. This is something that you have also mentioned quite a lot in this conference. I think many more times than in previous AGB conferences that I had been, so good job. And yeah, as it's been mentioned, the progenitors, of these AGB stars are stars between 1 and 8 solar masses, and about 50% of them have a companion in the main sequence. How many of those reach the AGB phase as binaries is not very certain, but we can say that a significant amount, and we can use that. So, as you probably know by now, what I've been doing in the last few years is looking at the interaction products of these AGB binaries in order to learn about the nucleosynthesis that I already mentioned, but also about how AGB stars interact with their companions. Because these systems down here that take the nucleosynthesis signature that these AGB stars made inside can help us learn about the S-process signature of the AGBs, but also those models that you are all running to see how AGB stars interact with their companions should reproduce these orbits at the end. Whenever we get to that point that we can evolve hydro long enough to see if the periods look like this. So what do we know about these objects? This is the famous or unfamous eccentricity period diagram that has been shown a couple of times. We know the orbits of about 130, 150 barium and related stars. We also know their chemistry. This is the sample by De Castro that has been completed by Roritz in the last few years. It's the biggest and most homogeneous sample for which we have chemistry of heavy elements of all these targets. It's about 180 systems in those plots. And we also know the masses of both the polluted stars, that you have the mass distribution of the dwarfs and the giants, specifically for the barium stars, but we have masses for a few CMPS as well. And we have the masses of about 60 white dwarf companions combining radial velocity and Hipparcos Gaia catalog of acceleration, so astrometry. The problem is that, well, it seems we have quite a bit of knowledge about these systems. The problem is that the overlap between all these 4 plots that I showed you is maybe 30 targets. Most of the work on the orbits has been done in the Northern Hemisphere with Hermes and Mercator, and most of the chemistry in the papers of De Castro, so the largest samples of AGB products, of AGB binary products, has been done with ferros. So north, south, not a lot of overlap. So at some point I was like, okay, can we add more targets, but in an homogeneous way? Can we find an homogeneous sample of these targets in a way that something gives us all the information? Because only like that we are going to be able to answer statistical questions like how many red giants are barium stars. I'm sure that some people in this room has a 1% number in their head, and I dare you to find the reference where that is written, because we say that 1% of red giants are barium stars, but it's not easy to find where that comes from. So that's the number I was hunting for, trying to find a more homogeneous sample of these targets. So as Sophie already said on Monday, we are in the era of large spectroscopic surveys. So, pick your favorite. I did a lot of reading to see which one was my favorite for this. And I decided to stay with Gala for several reasons. First one, the resolution is not as low as others, but also because it gives you abundances of 32 chemical elements, including 8 S-process elements. That's something you don't have in other surveys. Like all the papers that you see coming from Gaia, for example, on these wide Earth binaries polluted with S process depend on one element and one line. So let's not throw to the trash all these decades of star by star careful chemical abundance. Let's be careful with the service that we pick to make our biggest statements. So I work with Gala. That's Gala DR4 for you. I did some cleaning. These are the targets in Gala that they themselves flagged as good spectroscopic candidates for spectroscopic science cases. And then is when I start making choices to end up with a final catalog of polluted targets. And every one of these choices that I made changed the final catalog. So I'm looking forward to hear what you think about the choices I made in case you disagree fundamentally with some of them. As I said, Gala gives me 8 S process elements. I stayed with 4. I didn't want to stay with 1 only because that was one of the strengths of Gala, right? It will be silly to go to the survey that gives me more and then stay with 1. And I picked 2 light S process elements and 2 heavy S process elements to be able to do statistics of the S process, not relying on a single element. I also chose these 4 because I minimize the losses when I go to the good quality flags that the survey gives me. And they all have more than one line to work with, so we remove those systematics of working with a single spectral line. The goal, the thing I was going for, you can perhaps disagree if this was the good approach. I wanted purity over quantity. I wanted that if I tell you this star is a good candidate for a barium star, you need to do a little bit of an effort to prove me wrong. I didn't want to find them all and then discover that 20% of the catalog is just crap. So the first thing I wanted to do, because I come from the high resolution school, so I didn't want to trust the medium to low resolution, I built a high resolution sample with Hermes and UVerse data to try to see if I can trust the abundances of Gala. We did this for the temperature, first for the stellar parameters. So we computed the parameters and the abundances for those 4 S process elements that I'm going to work with the high resolution data and Gala. Here you have our differences. So in the temperature, I don't know if you see well enough the labels, but this is the yellow region shows 100 Kelvin dispersion. So most of the targets agree with Gala, and ourselves agree within 100 Kelvin. For the log G, we don't do very well. If someone can help me understand why, I will appreciate it. And for the metallicity, we again are quite happy with the results. So temperature and metallicity in Gala versus our high resolution job agrees quite okay. Let's see the effect on the abundances. And here you have the 4 elements that I decided to keep. So you have yttrium, zirconium, barium, and lanthanum. And the yellow regions here, in case you don't see the axis, is on 0.25. I chose that number because that's the threshold that was put, for example, in the Castro 2016 to say if something is a barium star or not. So if they flag as a barium star if the abundance is higher than 0.25. So I thought, okay, if Gala and I agree within 0.25, then I could be happy with the result. So that's what the yellow region means. We do better for some than for others, but there are no big offsets that all elements are in the same direction. So we took from this that we can trust the survey. So let me show you the catalog. And again, more choices. So every choice that I made will change the final number. So again, looking forward to hear what you think about these choices. I called S process enhanced stars, those stars that have the average of the 4 elements higher than 0.4. That's the number that traditionally would have been 0.25, but I stayed with 0.4 to be a little bit more conservative. And I did put cutoff on each one of the individual elements in 0.25. Because I found that using only this, I encountered some stars with negative barium, which I was not very comfortable with. So I decided to put this additional threshold there. So that's the catalog in the metallicity temperature parameter space. Something I liked to see is that I do not find many barium stars or barium star candidates with positive metallicities. I put no cutoff there, but that's what the S process models are telling us that I should find, right? So that's a good sign. And here you have the S process overabundance distributed with as a function of metallicity. I'm looking at Sophia. I was hoping for a warning, but am I doing well in time?
6 minutes.
Oh, okay. I'm speaking much faster than I thought. And this is the distribution of the second peak of S-process elements over the first peak. And this blob here on the right at higher metallicities overlaps very well with the data of De Castro, Roriz et al. So that's the slope agrees very well with previously known barium stars and also agrees quite well with most models that I found. So I am quite confident that these guys over here contains a high percentage of S-process polyethylene coming from AGB nucleosynthesis. This other blob over here could be the CMPS. I'm looking at the low metallicity people to see what they think, because I think the blob is a little bit lower than what we'll expect from models. But at low metallicity, our high resolution sample did not have a lot of stars. So I think we need more spectra, like real high resolution spectra to confirm this. But with the stars in the first blob on the right, I was quite happy with those. Then some statistics. I find 0.62, so no 1%, of the sample being enhanced in this process. I was a bit more conservative than literature choosing these stars. So, I mean, we can play, if we go to the traditional CATs, which I do not plan to do, we reach a number up to almost 3%. So we can play with the numbers until we get that 1% if you guys want. Something else I found that I liked is that the occurrence rate is the same in the giant and in the main sequence phase, which I don't think it agrees with what we've seen now. Like, we know many more barium giants than barium dwarfs, but I've been several years saying that that's just an observational bias against the dwarfs, and I was very happy to see that Gala agrees with me, because the numbers are very similar. And then finally, binarity. I could not be the person speaking the least about binarity in this conference. So I will tell you that 150 of these stars have a positive binary flag in Gaia, but you've seen the period eccentricity diagram of these systems, right? Gaia doesn't cover these orbits, so I'm pretty sure that most of them are binaries, and that if we started monitoring them, we will know for sure in a few years. In fact, a few of the targets that I observed for the high-resolution sample are being monitored thanks to Hans, and we do see binarity in targets that Gaia doesn't see binarity. So in that sense, I'm not very worried. So this is what I did. Yes, this is the summary. I originally just wanted to find more and find them in a way that I could, thank you, that I could find them, that I could characterize them homogeneously, so relying only on what Gala already did. But yeah, we did it making sure first that we can trust the survey, which I really recommend that people do. We have a more complete picture of the properties now. We will have when I analyze all this data. And just a reminder of why AGB stars should care about these targets, but also galaxies, of course. So thank you for your attention.
Good, yeah. Any questions? Yes? Thanks a lot, Anna, for the great talk. I'm not disputing your choices. I just would like to know why, if you have 8 abundances, why only use 4 of them?
Because every element that you add comes with a flag that Gala themselves are telling you how the neural network performed. And the more elements you add, the more stars you lose. There are few stars that have the 8 elements computed. So we played with it a little bit to see where we had equilibrium, and I decided to stay with 4. Okay. But if someone recommends a change of an element or yeah, I will be happy to.
I mean, I would just say if you have for the ones where you have the UV spectra, I would at least compare all the abundances with a high resolution to see which ones are the most consistent ones, maybe. Yeah. But yeah.
I think we computed them. I don't have them, but I think I should have the abundances. We also have a problem. I don't know if you noticed, but some of the comparison plots are missing some stars, and it's because I started observing these targets when Gala DR3 was out, and the catalog changes a lot from Gala DR3 to Gala DR4 because they fully changed their methodology. So yeah, but applying for UVS data requires some patience. So I don't think I want to apply for more right now.
Any other question for Anna? Yes, Hans?
Thanks for the talk. Do you see the clump in the red giant branch? It's an overdensity where the clump is no?
See, I think I do. I did not specifically checked, but I think I do. To separate the giants and the dwarf, I use the Gaia color magnitude diagram in some proper way, but separating the clump from the red giant branch is more difficult, so I don't think I will try, but I do think I think there is an overdensity that I can check with just a cat on log G maybe.
Yeah, actually, that sort of reminds me. Have you cross-checked against any astroseismology measurements of the stars in your sample? Because some of the glass stars have also been measured with astroseismology, so that would tell you more about the
evolutionary state. I've not done it, but I could. Yeah.
No, that'd be interesting.
Yeah.
Okay. Thank you very much, Anna. Thank you. And now, last talk of this session by Pavel.
So, hello everyone. My name is Paweł Kryński. I'm a PhD at ULB, and Lionel is my promoter. So we have, over the past few days, we have talked a lot about CMPA stars, about barium stars. So very quickly, how they are formed. We start with two main sequence stars. The more massive becomes an AGB. It synthesizes S-process elements, which are somehow transferred onto the companion. Eventually, the AGB becomes a white dwarf, and now you only observe the polluted companion, which we call a barium star or a CMPS star, etc. So when you look at the periods, at the eccentricities of barium stars and other stars that are formed through the same scenario, we say that they have periods between 100 and 10,000 days and eccentricity up to 0.8. And this is actually a big problem, because according to the classical binary evolution, we should observe those kind of stars in the blue shaded regions. So we should have either long period systems that have been widened due to fast winds. For periods below 10,000 days, tides are very effective, and we should observe only circular systems. But the biggest problem actually comes for binaries below 4,000 days, because given the very big radii of AGB stars, for those periods, the AGB should undergo Rochlop overflow, very possibly through the unstable channel, which should lead to a common envelope and very short periods in the end. So that's basically the LOCP problem. How do I want to maybe try to explain a bit this discrepancy? I want to study mechanisms that can shrink the orbit and increase the eccentricity. How do I want to do that? I want to use the binary evolution called Bean star, which tracks the evolution of both stars and of the orbital parameters. I focus mainly on the simulations of two M-Sun AGB with a one solar mass companion and at a solar metallicity. I want to include two mechanisms, the Wien-Rochlop overflow. So we have already talked a lot about it, where you have slow winds that are focused towards the companion. A fraction can be accreted by the companion. Some can be actually escape behind the companion, carrying extra angular momentum. So this will lead to orbital shrinking. And also a fraction can be used to feed the C circumluminary disk. And then in the presence of the disk, the binary will exert a torque on the disk, and the effect on the orbit is that eccentricity will increase. So just keep that in mind. So I will show you just an example track, because I will show a lot of them. So here I consider only Wien-Rochlop overflow with a binary where the wind speed is of 10 kilometers per second. We start at an initial period of 8,000 days and 0.1 eccentricity, and the winds very efficiently extract angular momentum, so the binary shrinks. Meanwhile, also the tides start to circularize the orbit, and eventually eccentricity vanishes. At some point, the binary is close enough to trigger Rochlop overflow on a circular orbit. Here it undergoes a stable channel, but the eccentricity remains zero. I simulated a grid of binaries with periods between 4,000 and 16,000 days. The red tracks correspond to binaries that have shrunk without triggering a Rorschach overflow, and the orange ones have first circularized, then triggered Rorschach overflow. So it is still for a wind speed of 10 kilometers per second. The black line here corresponds to like an approximative limit where a AGB of 450 solar radii will overflow. So 450 solar radii is like the typical maximum radius of 2 solar mass AGB. So wind rush overflow can be very efficient at shrinking the orbits. We can populate here periods above 4,000 days. We find some eccentric binaries in the end that did not undergo rush overflow, but many are circular. So still the problem of eccentricity remains. That is why we also include a circumbinary disk. So here is the upper track is just an example with a circumbinary disk. The circumbinary disk forms early on the AGB. The eccentricity first increases, and it is efficient enough so that even when the stars come close together and tides become dominant, Rorschach overflow can actually occur on an eccentric orbit. And this is something quite new, unusual, interesting, because usually we expect Rorschach overflow to be on a circular orbit. The orbital evolution is also quite interesting. And here under the assumption of conservative Rorschach overflow, meaning that basically all the matter from the AGB is transferred to the companion and nothing leaves the system, the orbital evolution will depend on the mass ratio. First, when the AGB is still more massive than the companion, the period and the eccentricity will decrease. Once end of mass is transferred, the mass ratio inverts, and actually the period and the eccentricity start to increase. So at the end, we find that even eccentric Rorschach overflow can preserve eccentricity, and even we can find even more eccentricity. So it's a very interesting mechanism that goes exactly in the way we want to. So now just for the grid of simulations where both mechanisms are included, I want to focus here on the green tracks, so binaries that have undergone eccentric Rorschach overflow. We find that their final orbits are between 0 and 0.3 eccentricity, so we have some eccentricity at the end. But we have another problem, which is that because during the Rorschach overflow, at some point when the mass ratio inverts, the period increases. So this actually prevents those binaries from going to periods below around 4,000 days. And they start to accumulate close to the line, to the black line. So how can we go even below? Super. We can relax the assumption of conservative Rorschach overflow. So now I assume that 75% of the mass actually is not transferred to the companion, but escapes behind it in a similar fashion as the wind Rorschach overflow. So it will carry more angular momentum and the orbit will shrink. In that case, if you can still consider like the stable, non-conservative eccentric Rorschach overflow, we can bring the periods down to 2,000 days and still have some eccentricity. Another mechanism that is quite often invoked when trying to explain very weird orbits is the tidally enhanced winds mechanism, which remains quite unconstrained. The explanation is basically the companion weakens the gravity at the surface of the AGB, which allows matter to escape more easily. So wind mass can increase even more. In that case, I have let the wind mass loss to increase by a factor up to 15. So there are multiple effects, but the main one is that due to the higher mass loss rate, the binary evolves faster and it will reach actually smaller radii than without this mechanism. So with smaller radii, it can also, Rorschach overflow can also occur at shorter periods. So here, for example, instead Rostov overflowing at around 450 solar radii, it occurs with, as in binaries, as in AGBs with 350 solar radii. So invoking this, I can bring down the periods to 3,000 days. Just I wanted to compare the results to the observations. So it remains quite obvious that there is a lot of work that remains to be done. Including our mechanism, the Wien-Rostov overflow and circumbinary disk, we can explain only the eccentric periods of barium stars down to 4,000 days. If you assume also some degree of non-conservativeness or tidally enhanced winds, we can go below to 3,000 or 2,000 days, but even those are quite generous assumptions. So it means that there must be something else still happening, and we don't know what yet. Okay, so this just brings me to my conclusions, which is that Wien-Rostov overflow can efficiently shrink the orbits. If you also include a circumbinary disk, this can open the pathway to a new mechanism, which is the eccentric Rostov overflow. There is also a lot of very interesting stuff that happens there. But basically, it's that we can still retain some eccentricity. Those mechanisms that we proposed until now cannot still explain the relatively short periods of barium stars. So the usual conclusion is that we still need more simulations. We still need to better understand maybe how the Rostov overflow actually works, maybe in the very weird atmosphere, with the very weird atmospheres of AGB stars. So there's a lot of very interesting stuff to still be done. So thank you.
Thank you very much, Pavel. Lynn?
Thanks, Sophie. Thanks for the nice talk as well. I have one question that applies, I guess, to all of your plots that you have been showing, and this is related to uncertainties in the sense that how have you implemented the mass transfer efficiency, angular momentum transfer, your eccentricity pumping mechanism, and then the last one, your tidal winds. You know, these are related to prescriptions and they are uncertain, I guess. How do we do that since we have so few understanding of how it actually works? So have you played with our unknowledge to see, you know, what range on these predictions that gives?
So thank you for the question. It's very interesting. There are certain parts that are very uncertain. Some are more or less better constrained. One of the most important mechanisms here is the Wien-Rostov overflow and the shrinking of the orbit. From my understanding, the simulation, the SPH simulation, start to agree quite well over how much angular momentum is actually lost. So I don't expect this to change a lot. So for the accretion efficiency and all the other parameters, very often they're used as free parameters, but they do not change like the philosophy of those results in the end. One constraint that you can use is, for example, for the circumbinary disks. So the strength of the interaction depends on the mass of the disk. The observed disks have masses below 0.2 solar masses, so this was one of the constraints that I tried to implement.
And so what are the typical uncertainties on the predictions that you have shown?
So for a very wide range of parameters, we can reproduce the same kind of plots. They have maybe different tracks, but in the end, it's very similar. So it's very hard to say what is the effect of different parameters.
Thank you. Yes.
Thanks for the great work, Pavel. I had a question regarding, so you say that you enter the Rostov overflow regime when you have when the filling factor is 1 at periastron, right? And in this case, I guess you compute like a net torque of Roche-Lobe overflow near periastron plus win Roche-Lobe overflow for the rest of the orbit.
Yes, yes.
And in this case, I have trouble to understand the pumping of the eccentricity on the very first plot you showed where you had this situation. Yeah, like this one. The huge pumping at of the eccentricity once you get the inversion of the mass ratio, is it triggered? Does it require the circumbinary disk?
No, so for the green part of the track, it's only the Roche-Lobe overflow where the mass transfer is so high that it completely overshadows all the other mechanisms. So I'm not sure what is the link that you try to do with the circumbinary disk.
So here the torques are quickly dominated by Roche-Lobe overflow.
Yes.
When Roche-Lobe overflow becomes negligible
Yes,
once you have Roche-Lobe overflow at periastron. That's the question. Okay.
Yeah. Because of the very strong mass loss rate. Mass transfer rate.
Okay, thank you. Yes, Shazrin?
One of the things about the circumbinary disks, if I remember correct, was that, well, I guess my question is how long do you need it to be there in order to do the pumping? Because I think when it was looked at earlier, it was that the circumbinary disk didn't last long enough to actually pump the eccentricity to the values that we needed.
Yes. Thank you. So the way I model the disk is also quite particular, in the sense that I have modeled the 1D structure of the disk, where I included viscous equations for the diffusion of the disk. I included the resonant interactions, and just I added the mass at the inner rim of the disk. So when you solve the equation is in this state, actually you have a lot of mass that is that accumulates near the inner disk of the rim before it is diffused outwards. So this gives a much stronger interaction between the binary and the circumbinary disk compared to the other models that people have already used and where the disk is already relaxed. So this is also one of the factors that allows this very strong interaction during the AGB without requiring very strong disk masses.
But thank you. It's a hard problem, so good that somebody's working on it. Thank you.
Thank you. Thank you very much. I think we can go on with the discussion in private discussions later. And so I would thank all the speakers of this morning session. And now I think we go for the discussion, Franz.
Is the slide up? We have 3 discussions during our meeting. 2 of the discussions are focused on the science presented in talks and posters, and this discussion here will look into the future of our instruments and tools. When I was arriving here, I was thinking back a little bit, and you see with this sequence of proceedings and posters that we can look back 20 years, 19 years. 2006 was the first incarnation of this Why Galaxies Care about AGB stars meetings. And if we think back, I think one can easily say that several of these conferences were really driven by significant improvements, both on the observational side, on facilities, as well as the modeling efforts. Sorry. We all remember, for instance, the first pictures Herschel provided us, these extended dust regions, the far infrared spectra, also ALMA and JWST, of course, among others, provided us with often surprising new insights. Or let's look on today's presentations with VLTI, often surprising or supporting earlier findings. ESO, the meeting sponsoring organization, is just busy with the Expanding Horizon initiative. With the completion of the ELT by the end of this decade, hopefully by the end of this decade, ESO has initiated now a process of selecting the next transformational facility, as they say, by a facility for 2040 plus. We, the community, are now invited by mid-December already to submit white papers with science ideas that really could drive these facilities. the idea of this discussion round is now to look into the future of our field, especially from the perspective of observation facilities. And of course, we will focus on new ESO facilities, but we also will have a look at other options, of course, to observe and also to model. But let's start with the ELT. Hans, where are you sitting? Hans van Winkel, you are involved into METIS. I have two questions for you. What do you expect from the ELT in this first decade of operation, and what next generation instrumentation for the ELT could be of special interest for us?
Oh. So METIS or the ELT in general?
For the ELT,
Yeah,
I
yeah.
would say
So
more in general.
it is
focused, of course, on our research
So what
question.
you have to realize, it's not a survey instrument. So the field of view is very small, and that means it goes very deep and very specific. What is unique to METIS in our field, I think, is the high contrast imaging, because with high contrast, you mean you can have very efficient blocking of the central bright star, and then you can look around what is there. And that, for binary introducing interactions, will be very important, I think. Together with a very high spatial resolution, there is also a high spectral resolution in the IFU. But to give you an idea, the IFU in METIS has a field of view of 1 arcsecond. So it's less than 1 arcsecond even. So you have very high spectral resolution in the near infrared, but with, so that's for chemistry very important. You can block the central star as well. And for circumstellar chemistry, that will be really a game changer, in my opinion. For the other instruments of the ELT, this, of course, it's more to the near infrared then. Then you have very high spatial resolution. Of course, it's a 40-meter telescope that will also be for resolved stellar population. That will be very important as well.
Mm-hmm.
So those two, I think, is high contrast, which is unique, and a lot of photons, of course, and high spectral resolution on very specific small regions. That will be, I think, the most important, let's say, additional instrumental added value of.
We can express wishes today.
Sorry?
We can express wishes.
Yes, absolutely. Yeah, so circumstellar chemistry, I think, will be very in demand, as well as very high contrast imaging.
Mm-hmm. Are there points, visions, ideas from the audience? What do we need? What we ask to have on the ELT?
If you ask now, then you have to wait, eh?
I know, but
because the first generation
for 2040.
The high resolution spectrograph, optical spectrograph, that will be the second generation. That will, of course, also be a game changer, where you can do abundant studies of resolved stellar population at a very long distance.
Of course, I was waiting for this point, yeah.
Yeah, I could not agree more. High resolution and going largely to the blue, where all the interesting element lines are located.
Okay.
Cubes will be on the 8-meter telescope. It will be not too far from here. I think the cubes will be.
I don't think the ELT is taking us to the blue.
Yeah.
And this.
But cubes is the VLT.
Yeah, exactly. It's VLT, but the ELT is optimized for the
red
other part.
Yeah. But for the blue lines, it's a high resolution spectrograph in the blue, very blue, much more efficient than UVS, and that's being constructed now, I think.
But that's on an 8-meter, not on the ELT.
If I can add, Andes will work from the B, but a goal is also to go to the U. It's not possible to go bluer than the U because the telescope is not transmitting, but obviously the blue is important, and Andes would be the only one instrument that on the ELT that can go so blue. So
I'm involved in Andes, and we are working on
It's a
this.
bit like espresso, no? Like it starts from 4,000 or something like that.
Yeah.
Farther blue. Yeah.
Yeah.
Yeah, I wanted to ask if anybody looked into Mosaic, which is for populations, which is the first one that will come online.
Not so much on science content, but more strategy. So what is smarter to do when applying for ELT? Because we won't be the only ones applying for time. Should we, I mean, we're 92 people in this room. Should we continuously submit 92 individual proposals, or should we prepare and coordinate, I don't know, consortia, or at least coordinated proposals I don't know what is smarter. What, I mean, with ALMA, it's always good to submit a lot of all stars proposals because we get fraction of submitted proposal time, right? But I don't know how it will be for the ELT.
Yeah, I was also thinking that maybe it's clever at least to organize some subgroups, you know, like I don't think the AGB proposals are going to go next to the chemically peculiar products, even though we are trying to answer similar questions, but I think it's a good idea to organize people interested in the chemistry or in other things and try to go as a team, yeah.
Really to identify the key topics and then maybe address. I think there's a lot of input already from this conference. What are the key questions? And of course, if we think then instrument-wise, of course, working together makes a lot of sense. And we see this, for instance, in large programs. And this brings me to the VLTI. I think we were presented today with fantastic efforts. Claudia, I ask you now not as the great host of this meeting, but as president of the European Interferometry Initiative. What is your take on the future of VLTI? What can we expect? What improvements would be bringing our field forward?
Well, there are several ideas in terms of concept for the 2040 for the VLTI. And I think one which is very relevant for us would be probably the kilometer baseline, because having basically more telescope and going to longest baseline, something that we could do instead of doing like the work on the convection on very few objects, we could extend that, for example. And then of course also the binaries. I think we should, so the community that is triggering this development is a community from extragalactic science and exoplanets and so on. So they will not go towards imaging very much, but from the VLTI side, from the what we have seen during these years is that we really need the images. Our objects are too complex, at least the AGB stars, they are too complex to go fishing into Fourier space. And we really need the images. So I think, I don't know if Xavier is around. No. Yeah, also some project where he wants to submit, where he's thinking also about in terms of imaging. But I think we can leverage from this effort. And for me, the big question will be like to try, I don't know, it sounds a bit crazy when I say it, but doing like how do we say, astroseismology, but with the resolved images. That would be one thing, and covering a parameter space which is much wider, and then the binary question. One of the big question, and maybe somebody, it was in the discussion of yesterday, but we didn't get there. Maybe we'll follow up tomorrow. Something that we should start to look into and sell it also, I think, to the rest of the communities as something relevant for us, is what happens to the solar system when we are on the AGB phase. And that is something that is a big question. The community is very hard to look at it because our stars are very bright. But I think that is also one of the questions that we maybe want to try to answer in 2040.
Are there other points in the field of interferometry from the audience here? Ah, here.
So there is an ongoing effort for a proposal for ESO in this call for ALMA 2040. There is the poster.
So I will come to ALMA as the next step. I was thinking of infrared. The next step is ALMA. We can.
It's still interferometry. So.
Yeah. It's all, yeah, of course. Sorry, I was not exact. It's infrared, of course, we could argue where infrared starts and sub-millimeter ends. Still something on the infrared side? Yeah.
Yes, so yeah, we will come to tomorrow on this, but also the post-AGB binaries, the circumstellar disks. I think, VLTI is also great for this. We also need imaging capabilities for the circumstellar disks, and this is very general. So it goes from protoplanetary disks to the post-AGB disks. It's circumstellar disks in general. But yeah, I think, in terms of that, a next facility having in the 2040s with very long baselines, the kilometer baselines would really help to understand the physics, in this community more on the physics of how stars actually die and how these post-AGBs in this case shape planetary nebula and the end of the life of the stars.
Thanks a lot. So let's move to the longer wavelengths. Of course, developing further ALMA is also on the ESO Horizon agenda. Liz, you have your post outside. You present already this initiative. Could you provide us with a few insights, what we can expect and what we can hope for an ALMA upgrade?
So thanks for the chance to talk about ALMA 2040. So as Tay already introduced, there is this ongoing initiative to produce an upgrade to ALMA that won't be taken into account with the current upgrade. So the current upgrade for ALMA is aiming to increase the bandwidth, the instantaneous bandwidth, by up to a factor of 4. So that's good for the continuum sensitivity, for spectral grasp, and also for speeding up spectral scans. But what it's not addressing at all is increasing the angular resolution of ALMA, which I think would be very useful or critical to many of the science cases here. Teo is leading actually the Sun and Stars science case for ALMA 2040, so I'm sure here he and many others working on this can comment better on the science. But the other thing which is not being addressed by the current upgrade and could be addressed by ALMA 2040 is a very dramatic increase in line sensitivity, so by a factor of 5 to 10. Now, that's not at all easy. You might have to add in like 100 more dishes to ALMA, but it could be well worth it again for many of the science cases mentioned here. So I think it's best if I pass it over now to the scientific people, so maybe you can describe better what science we could do.
No, please. Theo.
Well, I'm co-leading the working group. So I think one thing that I was thinking while we were talking about the other instruments before is that one of the things we were trying with this ALMA 2040 proposal was to characterize a bit things that we could do that are very far from reality now. And one thing that Wouter Vlemings simulated a bit is if we would get as much increase in sensitivity as we would hope, a factor of 10 or so, we could image hot Jupiters around red giant branch stars, which ties a lot to what Claudia was saying before. And it's one of the angles that we are trying to sell the evolved stars science is seeing what happens in systems with binaries and planets. And I would wonder the same for the other instruments, that maybe we should put some effort into estimating what type of systems we would be able to see with the imaging from the VLT and VLTI, and how these different things would cover parameter space that we would like to explore.
Or even related to the fate of our own solar system. That's of course also a good idea
exactly.
to sell it also to the politicians if they ask for money. Yeah, definitely. Any other points in that direction? I have another point. We are discussing interferometry now, but of course, what's about the large single dish up there? That is in discussion for quite a while, and I think this should also be thought about in this perspective. Somebody wants to say a few words on this?
I don't actually have much to say because I don't know. But there is this effort, we have APEX now, which has been doing amazing work for AGB stars. But although Max Planck is still running it, at some point that telescope has to shut down. But there's this effort, and it has been ongoing for years now to develop at last. Is it a 50 meter now? And will it stay at 50 meter? Yeah. Well, anyway, you know, they might get down, but up at close to the location of Apex now. But they don't have any funding from ESO, right? They get development funding in different ways, as far as I know. But it's a very active community, and I think, yeah, and they're proposing for the ALMA, for the ESO 2040 stuff, yeah. And I think it's important. We always think about this high resolution, ALMA, and getting higher resolution, but a lot of our basic work, we shouldn't neglect this. And it's important that we can have a new workhorse.
Exactly, yeah. Any other points in there, Silvia?
Just want to add to that I don't think one can see it as a replacement for something like Apex. So I don't think that the idea will be that very many people come with their small proposals. It's from the outset, it's been way more discussed as a survey telescope, although I think it's going to end somewhere in between. But if anyone is interested in getting in touch with that community, it's being led by Claudia Ciccone at the University of Oslo. So, I mean, there's a large high Z Galaxies component in there, but they are actually very keen on also getting local people in there. Well, local, you know what I mean, local diverse people. But, and another difference compared to Apex and ALMA, for example, is that for now at least, as I understand it, there is no super high spectral resolution capability planned for. Those are not the first generation instruments, unless I've missed something. But that also, for the people who are used to using ALMA and Apex or our standard meter telescopes now, it's a little bit of a different philosophy there. So it might actually tailor more or be more tailored to other people than our classic crew here that presents ALMA stuff. So have a look at it.
Thanks. Okay. Space telescopes were also important driver of AGB results. We're still using isospectra, Spitzer spectra. We remember, of course, Herschel. I mentioned Herschel already. HST, we had presentations on HST work, on JWST work now, of course. Marta, where are you sitting? Here, you have a microphone. You had the presentation that field. What do you expect from JWST or Roman? Roman was not touched here, or other upcoming space telescopes for our field of research. And of course, thinking about space telescopes, if you have wishes, these are the longest perspective, because from the planning timing of space telescopes, there we really look well into the future if you think about new things. So Marta, please. What's your take?
Yeah, I mean, right now we're in, sort of pretty decent shape in the near infrared and the mid infrared with things like Roman and JWST that will get us kind of right into the beginning of the 2040s. And then we also have Prima coming, which is going to get us mid to far infrared and much more sensitive than Herschel. And that one will get us to about 2040 also, maybe a little bit longer. And then beyond that, one of the facilities, at least as far as what NASA is planning, is the Habitable Worlds Observatory. And that one is, it's sort of optical to infrared, near infrared, but it's designed really, or it's advertised as an exoplanet telescope. But that means that, if you can resolve exoplanets, you can also resolve binaries, right? And so, so I think that that's something that this community could really take advantage of. And that one is supposed to be launched in the early 40s, 2040s. And then just some other thoughts. I mean, I was at this DUST conference last week, and then I came here, and at both conferences, people commented that one of the things that we need to think about is an infrared Gaia that would allow us to see the dustiest sources, also see through the ISM dust in the Milky Way. And then if we could get one that is very sensitive, that could get beyond the Magellanic Clouds, that, I mean, not for distances, but for periods, that would be amazing. And so I think there's a lot of things to think about that maybe we should organize our community around.
Yeah.
But there is a plan for a Gaia near, right? I mean, there is a proposal for this.
There's a proposal. That's
Yeah,
good because
yes.
But it needs
So
support.
this, as far as I know, it's also the people in Lund that are leading this. So David Hobbs actually presented this at an EAS a few years ago.
Yeah.
So there is definitely a plan to do this. Whether or not that then covers all the wavelengths that we would prefer is a different thing, but there's definitely something somewhere.
That's very good to hear. Yeah, yeah. And it would be nice to have something like that also with increased sensitivity to go much further. So yeah, I think that's great.
But we all know to get such a mission in one field, it needs a lot of community support because you see, you have call for ideas, then you have down selection, then you have study phase where still 3 missions compete, and then often for political reason, one or the other is selected. So I think it's quite good to really have a look at what groups propose, and yeah, and our community should have a saying there. If we can provide them with extra science cases, this is always a good thing. What we also saw during this meeting is that massive surveys, large data set, play a very important role, or even would say a growing role in our research. Often these massive surveys, of course, are not targeting AGB stars, but provide us with great information and keeps us busy for quite a while. We are now in the middle of the harvesting phase of Gaia. We saw results, and this is, of course, not the end of the story. We will do much more. LSSD is just starting. Michele gave some introduction on this. Martin, where are you sitting? Martin Kronewegen, yeah. What can we expect in the next decades in this field? And is there anything missing? Is there anything planned? There was already the mentioning of, for instance, an infrared Gaia that goes also in that direction. What about the future of ESO serving telescopes? Yeah, things like that. Yeah.
Well, I mean, LSST was mentioned, of course, Vera Rubin. I mean, just to give, maybe recapitulate on the capabilities, we'll observe half the radial of the southern sky, 8,000 square degrees. Every point will be observed every third day for 10 years. So, you know, that's another volume of data in 6 filters and a single visit limiting magnitude of 25.
Yeah.
I mean, for comparison, OGLE goes typically to 2021. The website said they want to target 17, or they will have 17 billion objects compared to Gaia, 2 billion. So that's a really another dimension.
And with this time resolution, of course.
And with a time resolution that's close to perfect for almost all types of variability. Also, you mentioned Gaia. Of course, Gaia DR4 is up in about 1 year. And it's not only that it goes from 34 to whatever, 66 months of data. I think there will be really new types of data products that are of interest, in the sense that the complete time series of all the instruments will be made available. So, of course, we know about the light curves of the variable stars. Now you will have light curves in principle for all the objects. So that's maybe not too new, but also all the astrometry will be made available. So you can fit your own astrometry model if you like. If you have, Gaia spatial resolution is 1 arcsecond, and your stars are binary and you have to observe it with an interferometer. Of course, more a priori data and knowledge, and you can fit your own astrometry model as complicated as you would like. And the same is true for the radial velocity instrument. Not so wide region, but pretty high resolutions surrounding the calcium-3 triplet, which now provides the radial velocity, typically an average radial velocity and an average spectrum. We had a little teaser, it was called the Focus product release 2 years ago, where they released the radial velocity curves of selected objects, including LPVs. But now we will have the spectra, and you can do whatever you like. You can redetermine the radial velocities at every epoch. And maybe more interesting is even these BP-RP spectra that were mentioned also by Michele and myself, which already provided a carbon star classifier for close to 2 million objects. Now you will have the spectra, which goes from the entire optical region, time resolved. So you can look at spectral variation and luminosity variation and, fit your favorite Comarx model as a function of time, or, it's limited by your imagination, I would say. And the third survey that I'd like to mention that was not mentioned yet is Foremost. As some of you may know, Foremost saw first lights in October, and the commissioning will take place over the next few months. And the first 5 years of Foremost, I should say, it's mounted at the 4-meter Vista telescope, so it's pretty big telescope. So the first 5 years are dedicated to surveys, both that were proposed by the community and, of course, the consortium surveys. And some of them have a clear, at least link to AGB stars. There are surveys on globular clusters, also surveys related to dwarf galaxies. And one that is really of particular interest called 1001 NC, led by Maria Rosa Cioni from Potsdam. And so this will observe 1,000 square degrees of the Magellanic Cloud system, targeting 1 million objects. And I asked her specifically, and since Maria Rosa was also involved in the VMC infrared photometric survey, so she actually plans to observe all known 35,000 AGB stars in SMC and LMC. Foremost has both a high resolution and a low resolution mode. Well, low resolution meaning 5,000 and high resolution 20,000. Okay, it will take 5 years. Of course, it's not public immediately. There are incremental data releases like for VMC, but we will have a spectra of 35,000 objects in the clouds. That would be a fantastic data set.
Yeah, thanks. One point maybe to add, coming immediately to us, is of course we are confronted with these incredible data sets now. During this conference, a few people already discussed machine learning. I think we have to enter the area of large language models and more general AI to deal with these data sets that I was really wondering. So this is very impressive. You had a point.
Sorry, nearby star negative Nelson here. I was wondering, since the Gaia near-infrared thing was mentioned, one of the problems we're having is that the nearby stars are all going to be saturated. Is there an option for us to get parallaxes for these objects? So a Gaia mid-infrared would be nice for that. Yeah. Okay.
Please.
Okay, this is actually a question online from a while ago, so going back to the ground, I guess. But Miguel Montajes has a good point on the question that Claudia was also mentioning on the solar system. It would also be, he says that this also offers a nice way to get closer to people looking for exoplanets with the VLTI. But I guess it also holds for an ALMA survey. So yeah, I guess combining multiple science cases and not only focusing on one. And this could also help reaching a critical size in terms of community. And if Miguel wants to say something, yeah, please feel free to unmute yourself.
No.
We cannot hear you, but you were unmuted.
Okay.
I said that thank you. After you cover
Maybe he comes back. Claudia, you had your hand up.
Are you going to cover the white papers part or not?
Excuse me?
Are you going to cover the white paper part for the 2040? Otherwise, I have.
We mentioned it already, and we can come back to it, of course, in the end.
Yeah, I just wanted to add, so for this 2040 call, it's not about the facility, it's about the white, they are calling for white papers. The deadline is the 15th of December, and we have to go with the scientific questions. So then everybody of us has its preferred PET facility, but we have to go with the scientific questions. And it would be very nice if you could try to organize ourselves exactly for what we were mentioning. So to get a critical mass and to try to, yeah, that's all.
Please.
So we hear about all these new instruments, which is really nice. But I want to mention, because we haven't done that yet, is that there is also an SKA coming. So I'm hoping that there's a whole new influx for example, OH. And I also want to mention the NGVLA, which is supposed to go all the way to the CO line, the 120. And you will have baselines of thousands of kilometers. So you'll get really detailed CO measurements there. And not only detail, but you can also use the angular resolution to go much further beyond what Gaia can do, and maybe even reach into the bulge, although we don't expect CO there.
Okay, thanks. That's very important, Ed. Last but not least, and especially interesting science question, we all know that these fantastic data sets, of course, have to be interpreted, and advancement in our understanding of AGB stars, of course, was dominated also by progress in modeling work, in physical description of the stars. Susanne, I don't see you. Here you are. What are the big challenges from your position for the next decade? What is missing, except more persons working in that field, of course? Like more instruments and so forth?
That's the main thing, actually.
Yeah.
We have very few theorists here, if you look around. But the point I actually want to make is, and I think that this is, I can see this evolution here. And we have now 3D in the title of the conference. I hope that by at least the 2 conferences on, we have 5D in the title for both wavelengths and time dependence.
Yeah.
And I want to stress this whole issue of the time dependence, both in observations and models, because this is where a lot of the physics is. To give a simple example, this is how you can distinguish between, is the blob caused by a binary companion, or is it a blob that is ejected from the star? And somebody also went back into single dish telescopes. So if you have to choose between physical consistency or between I mean, if computing time is a problem, then I would urge, don't throw out the time dependence. Go for spherical model if you can't do it in 3D, but don't throw out the physics, don't throw out the time dependence. This is, especially if you're looking at the first 10, 20 stellar radii, this is super critical.
Okay, so I think we had now, are there other points relating directly to modeling and theory, please?
I like time dependence. So I want just to point out that I was amazed by what can be done with this kind of 3D models when it comes to pulsation, to binaries, to circumstellar environments. And I was really amazed by what is observed right now. And both in many cases, but correct me if I'm wrong, both the models and the observations require a lot of time. So historically, stellar evolution is the time dimension of stellar evolution is studied with large numbers, so it turned into statistics. So I'm wondering, how can we capture the variety that we see and explore efficiently the space of stellar parameters that is increased by a vast number of dimensions now by combining the extreme realism of sophisticated 3D models with the efficiency of old-fashioned 1D approach. That's probably something that we need to start to think. It requires, of course, a degree, some degradation in a way of downgrade, let's say. Degradation is a bit harsh, but a downgrade of what can be simulated in 3D to be applied to stellar evolutionary track population synthesis models to capture what we see and what we are going to see. So this is something that we need to definitely something that requires a collaborative effort.
We heard also about these hybrid approaches, so that also could help in that direction, of course. So I think we saw now a very wide range of also science topics because they were presented to be carried out on future facilities and so on. I think we are now in the process that we could contribute as a community also to the white paper initiative. We know it's very short time now. It's 15th of December. But it would be kind of a Christmas present that this community here is at least supporting initiatives that are already there. It's clear we will not start here from scratch to write something, but we could really maybe single out a few of them, and we have still one more day. We can discuss also tomorrow. We have another discussion section. I don't want to misuse it, but I think we could, after this broad perspective now, maybe we can condense this in a few burning questions that are also realistically then addressed in the next 2 decades. Yeah. So I don't want to stop you now going for lunch and then for the excursions. Maybe Claudia has some announcements to make. And thanks for the discussion, of course. It was really nice.
Yeah. So something that we could just, sorry, before I close completely and I switch to the lock head, something that we could use, for example, is the Slack channel of the discussion, and the people could start posting their burning question, and then we could identify, we can submit more than white paper, more than one. So, well, the time is short, but so just for you to know. And so we could try to identify the big burning questions, and then people could say, okay, I want to contribute to this one. It's 3 pages. It's not a lot of work for 1 month. Okay, close parenthesis. So we are going to have lunch. It's a served lunch. So you will sit down and eat and not standing. Again. Again, yes, again. Yeah, it's me still, the Italian here. The buses leave for both the excursion to the vineyard and there is a smaller one, I guess, for the downtown. They leave at 13:50, so 10 minutes before 2 o'clock, sharp, at the entrance of Sepal. So sit down, enjoy your lunch, and watch out from time to time in your watch and start to walk towards the buses, I would say at 1:40. The latest. Enjoy.
Thanks.
Sorry? Well, I think because we're leaving from lunch, I would take it with. I don't know. I mean, I guess it depends on. I think most people will take it up.